So, just to summarize what we have done and to formally tell them that in the wrinkle flame regime we have got essentially the Reynolds number to be greater than 1 and the Karlovich number to be less than 1 and U primes by SL is less than 1. So, of course, this means that your flame thickness is less than the Kolmogorov length scale and the flame element retains a laminar flame structure within the turbulent flame suite. And since U prime is SL is less than 1, the flamelet surface is only slightly wrinkled. Okay. And in the corrugated flamelet regime, of course, you have Reynolds number to be greater than 1 and Karlovich number is still flame Karlovich number is still less than 1, but and your U prime by SL is as you see here in the corrugated flamelet regimes your U prime by SL is greater than 1. So, this is a typo, please correct it. Your U prime by SL is greater than 1. Okay. So, since your LL, that is the flame thickness, the preheat zone thickness is less than the Kolmogorov length scale, the flamelet structure is retained, that is a laminar flame, the flame element retains a laminar flame structure, and your U prime by SL is essentially greater than 1. So, the flamelet structure is highly convoluted. Okay. So, you can see here just to give you an example, here you see an eddy which is essentially rolling it, and you see here it is essentially first stretching it and then forming a fold, and this kind of structures are found in this corrugated flamelet regime. Okay. But in the reaction sheet limit, in the reaction sheet regime, when the Reynolds number is greater than 1 and the Karlovich number is the flame Karlovich number is actually greater than here also it should be greater than 1. Okay. In the reaction sheet limit, when the flame Karlovich number is actually greater than 1, I will just so this has to be greater than 1. Okay. And this flame Karlovich number has to be greater than 1. So, when the Reynolds number is this in the reaction sheet regime, when the Reynolds number is greater than 1 and the flame Karlovich number is greater than 1, but of course, the reaction Karlovich number is still less than 1. So, this means that Karlovich number greater than 1, as I have said, means that your LL is essentially greater than your eta. Okay, and your tau L is greater than tau eta. So, it means that essentially the AD is smaller than LL, which are essentially but still greater than eta, can penetrate the preheat zone for large eddies inside for large eddies flame is the flame is still a flamelet. Whereas for large eddies means that the eddies which are greater than LL, the flame still behaves like a flamelet manner. And the reaction sheet thickness, of course, this LR is less than eta. So, the reaction sheet is only wrinkled. So, the reaction sheet is like this, it does not change structure, whereas this AD has penetrated inside this, and this thing can change the structure like this. Okay. So, the preheat zone structure is changed, whereas the reaction zone structure is retained. So, this is called the reaction sheet limit. Okay. And this is very much of practical interest in terms of gas turbine engines, in terms of like SI engines, in afterburners, etc. A lot of those flames are essentially belong to the reaction sheet limit. Okay. Now, well starred reactor regime, that is typically not experimentally has not been well studied. It tells us that the Reynolds number greater than 1, then Karlovich number, reaction Karlovich number greater than 1, and the entire flow behaves like a well starred reactor without any distinct local flame structure. Of course, as you said that these are like loose boundaries to identify the flames, and even in the this limitation is that you see here we assume that the Kolmogorov length scales have are capable enough to effectively change the structure. Now, the Kolmogorov length scales are essentially these eddies are just prior to dissipation. So, the Kolmogorov eddies are very short lived, and that because they will be immediately dissipated. So, whether they carry enough kinetic energy to even distort the flame structure, that needs to be explored. So, anyways, these are just some guidelines about what kind of flames to expect in what situations, and based on this one can formulate different kind of models and apply different kind of turbulent closure models or reaction closure models. Okay. So, one thing just few comments about the interpretation of the Karlovich number and the Damkolon number. So, the Damkolon number helps in assessing the interaction of large scales of turbulence with the flame. Okay. So, large scales is of course of the order of the integral length scale, because Damkolon number, the flame Damkolon number is essentially given by your tau integral divided by tau flame or tau L. Okay. Now, whereas the Kolovitz number, and of course, the Damköhler number greater than 1 means that the flames time scales are smaller than the large time scale in turbulence, and it is difficult for large scales to disturb the flame structure. So, when Damköhler number is much greater than 1, your flame structure essentially retains the same property as that of a laminar flame. When Damköhler number is less than 1, it means that your eddies of the integral length scales are even can disturb the flame structure. So, when the Damköhler number less than 1 essentially means that the flames turbulence interaction can become very strong, and the interaction can span from the essentially the integral size eddies down to the smallest scales in turbulence. Whereas the Kolovitz number, it is interesting, it helps in assessing the interaction of small scales of turbulence with the flame, because the Kolovitz number is essentially, if you remember, the Kolovitz number is essentially the flame time scale divided by the Kolmogorov time scale. So, it essentially assesses the interaction of small scales of turbulence with the flame, and this helps in telling us that how much mixing it can do inside the flame structure. Okay, mixing of fresh reactants with the intermediates or the intermediates with the products, so and so, and all these sort of things it can tell. Okay. Now, and the Kolovitz number much less than 1 means the flame time scales are smaller than the Kolmogorov scales and turbulence, and it is difficult for the small scales to disturb the flame structure. So, these are the two limiting conditions, that the Damköhler number much greater than 1 and Kolovitz number much less than 1 essentially means something that the laminar flame structure, the exact laminar structure or the near bent laminar flame structure will be preserved. Whereas Damköhler number much less than 1 and Kolovitz number much greater than 1, this means that that essentially you are in a state where turbulence is very strong and it can disturb the flame structure at different levels, and when it disturbs the flame structure, the associated properties like diffusivity can inside the flame when it has to be considered, that is a turbulent diffusivity has to be considered, and can in certain cases override molecular diffusivity. So, this needs to be understood, but of course, molecular diffusivity has been shown by recent research that molecular diffusivity is still very important at all conditions when it comes to flames essentially, because at smaller scales the molecular diffusion again becomes very important when the large gradients are produced. Okay. Now, few definitions of flame speeds. Of course, as you see that the laminar flame speed definition that we have obtained, this laminar flame speed expression that we obtained, that was valid for planar laminar flame speed, but still that is gives you a very clear idea about how the flames should behave, on what factors it depends. And now, but for doing analysis in turbulent flows, we need to have different kind of definitions, from which suppose you have a turbulent flame solution, DNS data set. Okay. So, and from that how we will extract the flame consumption, the different flame speed. So, one is a flame consumption speed, which is given by the, if you integrate over the entire volume the fuel consumption rate and normalize that by rho times YF of the reactants divided by a reference area, that gives you the local flame consumption flame speed. Okay. And then also there is a definition of displacement flame speed, and which is defined essentially the way the flame is the flame speed is defined, that it is a local and it can be defined at any point, that it is it's the velocity of the flame surface with respect to the local flow field, okay, in the direction normal to the flame surface itself. So, Vf is the velocity of the flame surface. These are all in absolute in the laboratory reference frames. So, this is Vf is the velocity of the flame surface, and U is the velocity of the local fluid. So, if this is the velocity of the flame surface, the flame surface is, this is the flame surface, it is moving in with a velocity Vf, and this local velocity is U. Okay. So, then the resultant velocity of course is we get a minus U, and the resultant velocity of these two things of Vf and minus U is essentially given by Sd times n. Okay. So, then you multiply with the normal vector, you get Sd. So, from this also you can get, if you can track the flame surface. Now, here we need to introduce before we go into it, before we go into the other details about how do we model these things, how do we model turbulent or flames in turbulent flows. One important concept for laminar premixed flames that we need to introduce here is essentially called the concept of flame stretch. Okay. It is essentially the rate of change of area of the flame surface area with time per unit original area. Okay. So, as you this is important, because as you see that if you go back to the previous video that we shown, that we had shown, that you see that initially this surface area was planar, okay, and initially it was planar, and but you see this is planar, and then in the same cross sectional area it becomes convoluted, it becomes distorted. So of course you can understand this at a later time. The surface area of this convoluted surface is much greater than the initial planar surface area. Okay. So of course then the surface area is increasing, then the surface area is increasing because of the stretching action of turbulence. So this in premixed flames and even to some extent in non-premixed flames, the flame stretch is a very important concept. Okay, it's the rate at which is the rate of change of area per unit original area. And premixed flame, as you know, can be sensitive to non-uniformities of the flow and flame curvature and flame unsteadiness, and the effect of all these things, that is, why does the flame area change? The flame area actually change because of these things, that is the non-uniformities of the flow. It changes due to flame curvature, it changes due to flame unsteadiness, and all of this effect of this non-idealities over a flame can be quantified through the stretch rate of a flame. So actually it is the 1 by is actually the, you will see that the stretch is essentially 1 by a dA dt, but this change in the area is affected through this things like the non-uniformities of the flow and curvature and flame unsteadiness. So as you see here that the flame stretch is defined as 1 by a dA dt, where a is the area of an infinitesimal element on the surface. Okay. Now and this is quantified, of course I will not derive it, but you can take a look into Professor Law's book for the derivation of this thing, where this flame stretch defined by kappa is actually defined as the sum of two quantities, that is, it's the sum of the tangential straining rate on the flame surface, which is given by this quantity, okay, and it's essentially the strain rate when you project it on the tangent to the flame surface area. So strain rates can be obtained from the flow strain rates, as you know, Sij is equal to dy half of dy dxj plus duj dxi, and when you project this along the flame surface area. So what I want to say is that the strain rate in a fluid is essentially Sij is half of dy dxj plus duj dxi, okay, and then if you have a flame surface like this, so if this is the normal and this is the tangent, tangent can be in any arbitrary direction on the surface. So but suppose you choose a particular direction of a tangent, so the tangential flame stretch on that is given by when you project Sij onto along the tangent, and that is given by this quantity, okay. And so this is important, because when you have flow non-uniformities, actually what it means is that tangential strain rate is what it means is that, so if you have a velocity on the flame at this point which is this, and at this point which is small, so of course this point of the flame will move much farther than this point. So essentially after some time, then this surface will look like this, okay. So this point has maybe has moved here, and this point have moved here, okay. So as you see that this leads to growth of the surface area, whereas if all points on the flame tangent, if they move with the same velocities, then there is no flame stretch. So the flow non-uniformities, okay, flow non-uniformities along the tangent is what create this tangential strain rate. It is very intuitive that you are basically on a surface, if you have different, if you push the different parts of a surface differently, then of course this can lead to extension or contraction of the surface, and that is what is quantified by the tangential flame is quantified by the tangential strain rate. All right. And the other thing is that when you have curvature, suppose you have a similarly you have a flame which is a spherical flame which expands. So of course after expansion you will see that this point has gone here, this point has gone here. So of course this thing has even if there is no flow non-uniformity, so you see that because of the curvature, this part of the flame segment has become like bigger, and as a result of that this is essentially causing stretch also. So stretch essentially increases the surface area, or it can decrease the flame surface area also. That if the flame stretch is positive, it will increase the surface area. If the flame stretch is negative, it will reduce the surface area. And this is essentially, as you see, is quantified by two things, this tangential surface area, tangential strain rate, and the tangential strain rate and the flame speed times the curvature. So these are the two things. Okay. So in the next we'll take a break, and in the next class we'll basically come back into discussion about the different models for turbulent combustion. Thank you.